Welcome to The Explainer. Okay, let's dive into this. We all know that large language models have completely flipped the script on how we interact with information, but they have one massive fundamental limitation, right? Their knowledge is completely frozen in time. They literally only know what they were initially trained on. To fix this, developers have been using Retrieval Augmented Generation, or RAG, to connect AI to external, up-to-date knowledge. But as you'll see today, the way we currently build that memory is hitting a massive wall. Here's our roadmap for today. We'll start by looking at the limits of AI memory, then we'll break down how vector RAG works and unpack the graph RAG revolution. After that, we'll put them head-to-head before arriving at our ultimate destination, the hybrid architecture. Let's get right into it. Section 1. The limits of AI memory, where standard retrieval hits a ceiling. If you're a developer or a system architect building agentic AI right now, I guarantee you're already feeling this exact pain point. So here's the big question. Why is RAG failing at complex, multi-hop questions? Look, standard RAG absolutely makes large language models smarter. It's great for factual queries, but the second you ask an AI to perform complex reasoning, to really connect the dots across multiple different documents, it just falls completely apart. And this brilliantly illustrates exactly what we're talking about. On the left, we've got a simple query. What is the refund policy? Standard RAG handles this beautifully because the answer is probably just sitting in a single paragraph somewhere in your docs. But look at the right side. Which teams own the datasets feeding the customer churn metric? To answer this, the AI has to find the churn metric, trace it to a specific dashboard, trace that dashboard to a dataset, and then finally link that dataset to a specific team. It has to traverse 4 connected entities. It's a multi-hop problem, and standard RAG just isn't built for it. Section 2. How vector RAG works, the semantic cloud. To understand why that multi-hop question completely breaks standard systems, we really need to look at our baseline technology first. Okay, so vector RAG works by representing data as dense, mathematical vectors. Basically, it takes your text and plots it in this crazy, high-dimensional space where geometric distance equals semantic similarity. Think of it like a giant, fuzzy semantic cloud. It's kind of like searching for a book by remembering its cover color. It's fantastic for finding things that are related in meaning, but it completely lacks a strict, explicit roadmap of how things actually connect in the real world. So when it needs to jump across specific concepts, this fuzzy matching just loses the plot. Section 3. The graph RAG revolution. Adding explicit structure to knowledge. Now we're getting to the fun part. This is how we actually fix that multi-hop bottleneck. Graph RAG fundamentally changes the game for how AI memory is stored. Instead of that fuzzy cloud of numbers we just talked about, it represents memory as discrete entities, which we call nodes, and explicit relationships, which we call edges. So, picture a node for a person and a node for a company, connected by an edge that literally says works at. Instead of crossing your fingers and hoping a text chunk is semantically close to your prompt, GraphRag gives the AI exact structured context. It explicitly follows the paths between connected ideas, no guessing required. So, the crucial point is how we actually build this pipeline. It happens in 4 logical steps. First up, entity extraction. An AI reads the raw text and pulls out specific people, places, and concepts. Second, relationship linking. It maps exactly how those entities connect to one another. Third, community detection. It uses algorithms to group heavily connected nodes into distinct clusters or communities. And finally, community summarization. It generates high-level summaries of what those communities represent. It literally transforms messy, unstructured text into a highly organized knowledge graph. Now, I definitely don't want you to just take my word for it. Let's look at the hard data. This quote from Microsoft Research shows just how massive this architectural shift really is. They found that by using explicit paths instead of fuzzy math, GraphRag improved the comprehensiveness of answers by 50 to 70% on complex tasks that spanned multiple documents. 50 to 70%. That is an absolute staggering leap in performance for AI agents. And the benefits don't just stop at giving you more comprehensive answers. A 2024 Stanford study looked at knowledge-intensive tasks and found that graph-augmented retrieval resulted in a 35 to 45% reduction in factual errors on multi-hop benchmarks. Think about what that means. When your AI agent relies on an explicit map of relationships, rather than just guessing based on semantic proximity, AI hallucinations are drastically reduced. It's just way more trustworthy. Section 4. Vector versus graph comparison, the head-to-head showdown. We know what they both do now, so let's set up a direct feature-by-feature battle. Now, what's really interesting about this slide is the direct contrast in logic. On the left, vector RAG is all about dense, embeddings, and fuzzy matching. It's fantastic if you just want to search for the general vibe or theme of a document. But on the right, graph RAG is deterministic. It gives you relational memory through exact nodes and edges. If you need to know exactly how a specific regulatory decision impacts a specific product line, you absolutely need the explicit paths of a graph. Let's look at some benchmarking data from Falc or DB that proves this mathematically. Draw your eyes to the complex reasoning column right in the middle. Standard RAG scores a 42.93, but the Falc or DB graph RAG implementation completely blows it out of the water with a 58.63. Overall, the graph-based approach vastly outperforms the standard vector approach whenever the AI is asked to truly think and reason about connected data. It's not even close. So, does this mean we just throw our vector databases in the trash? Absolutely not. Section 5. The hybrid architecture, the pragmatic reality for agentic memory. The true solution here isn't to rip and replace, it's to combine forces. Hybrid search merges the absolute best features of different algorithms. It takes exact keyword matching, like BM25, dense vector embeddings for that semantic understanding, and graph traversal for relational logic, and fuses them all together. This overcomes the limitations of any single approach, giving your AI agents maximum accuracy and incredibly rich context. Let's move to and see how this builds an amazingly powerful pipeline in practice. Step 1, a user asks a question, and the vector database steps up to the plate first. It performs a semantic search to really quickly locate the most relevant entry nodes within a massive dataset. Then, step 2, once those starting points are found, the system dynamically shifts into graph traversal. It literally walks the explicit edges connected to those entry nodes to extract the precise relational context. You are getting the broad, fuzzy recall of vectors married perfectly to the strict, deterministic precision of graphs. It's brilliant. To really grasp the real-world impact of this hybrid scale, check out this recent medical research case study. By integrating genetic databases and clinical trials into a graph, researchers mapped out 1.6 million queryable relationships. 1.6 million! Using multi-hop queries, the AI was actually able to uncover previously hidden connections between genetic markers and Alzheimer's treatments. This isn't just a neat little tech trick. This architecture is literally accelerating hypothesis generation and pushing medical science forward. Which leaves us with this final thought. As your AI agents continue to scale, will their memory rely on a fuzzy semantic cloud or a strictly structured hybrid map? The data clearly shows that explicit relationships are the key to unlocking true reasoning capabilities. Thank you for joining me for this explainer, brought to you by Synthetic Minds by Shahid. It's time to start experimenting with graph structure in your pipelines today. See you next time.